So the first speaker is Professor Peter Wriggers. Peter, you should have the power to share your screen.
Yes. Can you see
Excellent.
it?
Yes. Yeah. So Professor Wrigger is going to talk about application of virtual elements for simulation in solid mechanics. Thank you.
Thank you very much for the nice introduction and also for inviting me to this very interesting, for me as an engineer, very interesting and inspiring meeting so far. I will give you today some thoughts about what we as engineers can do when we basically look at the virtual element method. Of course, I have to acknowledge a lot of people from my group and also from colleagues we work together with from many different countries, but especially from Italy. So let me just start with, with a motivation, what I want to talk about. The thing is contact mechanics is one problem which we yesterday already saw in the talk by Eduardo. The other thing is fracturing processes, and I will talk about the goodies which you have if you use a virtual element method. Homogenization is part of my talk, which I want to look at. Something for large strains and large deformations, crystal plasticity. The word crystal already shows, if you can see here my little mouse, this is a crystal like this, which we are investigating that you really can use the virtual element method quite nicely. I was very glad that Franco yesterday talked about C1 continuous elements. We also had a look actually at it, and today you will not only get the theory, but you will also see some numbers, and it's very, very exciting actually how the elements perform as finite elements. And finally, I had the idea, and we are working together with Alfredo Gaineto from Brazil on using virtual elements in discrete element codes as sort of single elements which can sort of deform and are in contact. You see it down here. Now, I come from Lower Saxony. This is our arms, and while our ministry has sort of a big thing, you know, our horses learn about our powers, but I only put this picture because everybody knows from you that, of course, the virtual element method is ideally suited also to map into something like horses. What are the advantages for engineers? The advantages in my case are that we have an element with an arbitrary number of nodes. We can have a non-convex shape. This is great. UH is basically only defined at the boundary, and also C1 continuous ansatz functions are possible, which is good for Kirchhoff-Love plates and shells eventually. Of course, from the engineering point of view, there are some drawbacks. Engineers don't like stabilizations because they basically have some parameters which are not directly coming from the problem, from the physical problem, eventually. So you have to somehow find out that you don't get a solution which depends on stabilization. On the other way, stabilization is quite interesting for coarse grid accuracy. And the other thing, which is a little bit annoying, is that you cannot move everything to the boundary once you go into nonlinear problems. So you have to integrate over the elements. Now, what is my basic interest? I have an interest in non-smooth problems. Many of the engineering problems are non-smooth. Contact with friction, plasticity, fracture mechanics, they are non-smooth. And that means you need a method to solve these problems. Of course, we want to have accurate solutions, which would be adaptivity. And engineers like still coarse mesh accuracy. Because in 2D, it's no problem. You can solve 1,000,000 degrees of freedom on your notebook. But if you go 3D, you don't solve 100 million of degrees of freedom. So you have to have sort of a coarser mesh. You cannot always do the refinement. Either you use adaptivity or you have good coarse mesh accuracy. So for a real engineering application, this is somehow a little bit necessary, at least to my taste. Now, the implications of non-smooth problems, of course, are that we basically can use quite nicely low-order discretization schemes. Higher-order discretization schemes are always trouble. If you try to solve non-smooth problems using isogeometric analysis, it can be done, but you have to do a lot of tricks to come about it. The goodie, if you use low-order discretization scheme, on the other hand, is that your integrals, which you have to compute, and usually in our applications, the integrals depend somehow on gradients, then they are constant. So the integration also for nonlinear problems is not necessary. And so this is sort of an easy to implement method. What is also good with virtual element are the simple mesh refinement strategies, and about the stabilization I have already talked a little bit. Now, the advantages of the method in engineering applications, and actually my first, I think, connection to virtual element came when Franco gave a talk somewhere on some conference and talked about the virtual element method, and I immediately had the idea that contact problems could be solved with this method quite nicely, because contacts, we will come to that later, have different difficulties if you have non-matching meshes. And so from this point of view, a node-to-node concept can be used for unstructured meshes and also for large strain computations. This is quite nice. The other thing is, if you look at fracture mechanics, then your elements start to break up. And it's pretty easy to define new element shapes during a crack propagation. So this is also something why we looked at the virtual element method. Adaptivity, I think a lot of people have said this already. Hanging nodes are not inside some virtual element discretization, so this is fine. Homogenization is also a question. Crystals can be modeled with only one virtual element, which is great, but then of course you have to check whether it really works. Again, element design, C1 can, VEM elements can be, virtual elements can be sort of used as finite elements, as Franco yesterday pointed already out. So it's good to have a look at it, whether these elements are really performing well in some sense. And finally, the discrete element method. So these flexible particles, I think this is also something which one has to look at. And I will show some results in this regard. Of course, there has been a lot of work already, mostly in the mathematical community. And I just put here the beginnings because I cannot put all the papers which have been sort of written and used in with the use of virtual elements. I only put some papers here which basically go back to the problems which I'm talking about here in this case. So I left out a lot of things on fluid dynamics and magnetohydrodynamics and other things, which where the method has been also shown to be very effective. Now, I think in this kind of audience, I can skip these slides. I mean, this is all about the definition of the virtual element method. As I said, I am interested here in a low order ansatz. That means I use a polynomial of degree 1. Then I have to compute in the 3D case the projection, and this can be done quite easily because in the linear case, all the gradients of the polynomials are constants. And if you then use the Galerkin type projection, which is classically used, you can directly evaluate your gradient in terms of the boundary integral. And actually this gradient will basically already be the same as the parameters A, ij, which you need to compute in your method. So this is quite easy. An extension today for nonlinear cases for higher order elements is given by Blush today at 12:25. So this would be sort of an extension to what I'm saying here. So we can compute these parts, and then, of course, once we have the basically ansatz polynomial of the projection, which I call u pi. I think you call it usually pi of UH, so it's just a shortage of shorten the notation. We can basically compute the strain energy. I like to use the strain energy instead of the weak form. I think it's only a matter of taste. You can do whatever you want. The only thing we found out is we are using always what is down there, this automatic system, symbolic system to generate all our matrices, which was developed by Jože Korelj. And we found out that if you start from the potential, you get the most efficient code. Don't ask me why, but this is the case. And so that's why we like to use the potential. The other thing for the potential has this big advantage. You might know that if you go nonlinear in solid mechanics, you have as many stress tensors as you want and as many strain measures as you want. We use just the strain energy, like here, the W, and put in the right Cauchy-Green tensor. You don't even care about what kind of stress tensor you have. As long as you don't want to compute the stresses, you can just derive all your equations without even defining a stress tensor. Now, what we have to do here now, we have to compute this right Cauchy-Green tensor in our strain energy function, which can be done in this way, which is nonlinear in a sense. And here we put in our projection gradient u pi. And we can evaluate this, and we get this constant term, of course, depending via the on all the nodes at the boundary of our virtual element, the URE. And once we have this, we can just take this one and differentiate this with respect to the boundary nodes and compute the residual and the tangent matrix. And we are done for our virtual element sort of implementation in this case. Now, of course, we have to stabilize. Stabilization can be done also in different ways. I use also here the word penalization, which I think Franco didn't like yesterday. But it looks like, at least for me, if I write this as a sort of as an energy, that this is like the classical penalty term, which we have also in contact mechanics. But anyway, what we want somehow to penalize the deviation from the solution, from the UH, and this can be done. So you have here a parameter alpha, which you have to somehow choose and select, which also depends on your mesh size. Another possibility which we introduced to get a better coarse grid accuracy and accuracy for some of the, let me say, nonlinear problems was to use a difference between potentials. Also, this is consistent because the difference of the potentials once the mesh size goes to 0 basically vanishes, and you get the solution of the consistency term. Now, the problem with this penalization, which I call it, or you can call it the classical stabilization, which is always used, is that either you choose alpha equal constant, which does not really work for nonlinear problems, or you can basically make alpha depending on some variables, which eventually, like here, the stiffness matrix or the trace of the constitutive tensor. But this makes linearization a little bit complicated because you have then to linearize these terms, which is sort of messy. What of course you can do is you can keep them during each load step constant, and then you have some sort of a Newton method within each load step, but this eventually avoids to use large load steps. With the other stabilization, there is no problem. you have somehow to define this potential you had, but this can be defined also as the same potential which you use for the consistency part. The only drawback, of course, is here you have a potential which depends on UH. And now the question is, we don't know UH within the elements. So I thought about it to make basically a mixture of finite elements and virtual elements, where I use here finite element triangularization, which actually has the same number of nodes. So we do not introduce extra nodes. This can also be done in 3D and to compute the use the stabilization for our computations. This can be done, and there are some papers where we showed that this works, and it actually works better than just using the finite element approximation inside here, which would be obvious to check, right? Now, let's first go to contact problems. Contact problems, as I said, was sort of my beginning of the virtual element method, and also had some, in the beginning, a little bit of a problem to understand what was going on. But luckily, there was this hitchhiker's guide to the virtual element method, which really helped. We have done some work on small strains, on large strains with sort of classical approaches. And then we also use the curved elements, which were developed by Eduardo Artioli and Lorenzo Wriggers, and have done some joint work together. So what is the general thing if you are classically looking at finite element methods for contact? So classically, you have a node-to-node thing. But if you have a non-matching mesh, this doesn't work. So the next thing is that you say, okay, I have a node-to-segment contact, which you can formulate. We did it also somewhere in the beginning of the 80s. The problem there is that it does not fulfill some sort of a patch test if you have a constant load on the contacting surfaces. So this one basically does not lead to sort of constant stress when you basically use this in an interface. Of course, engineers have seen that, and then they introduce something like segment to segment or mortar methods, which sort of somehow alleviate these problems. But they are very complex and complicated. And so the good thing is that with the virtual element method, actually what you can do if you have a non-matching mesh, which are here the black nodes, you can do a projection from the black node of to the opposite surface and insert a node there in your virtual element, which is completely allowed and will give you a nice sort of approximation. So by doing this, we actually define something which is on the right side, which is some sort of a segment, which here is the original node, here's the projected node, and so on. And you can basically define the gap. You can define a linear ansatz in between the gap. If you use, or whatever ansatz you use for your virtual element, you can introduce here. And you can write the contact terms, which are down here. This is sort of a penalty approach where the gap function is squared times the penalty parameter, or you can use a Lagrange multiplier approach, or you can also use other approaches to solve this problem. So, and this is very nice because here this stuff is only acting on the boundary, so you can just insert your UH, which you have at the boundary. So from this point of view, it's a very nice method. And actually, it also fulfills all properties you want. And this is one example which was already shown yesterday by Eduardo. This is sort of a ball in a surface again. So it's a curved contact surface here. And if you use, for example, a node to segment contact here, then for a coarse grid, you get all these sort of jumps in the stress field. This is sort of the normal contact stresses here in this case. If you refine the mesh, then eventually you get the correct solution. Now, if we use our node-to-node contact with the curved method, with the curved elements, which were derived by Eduardo and Lorenzo, then you can see that even for coarse meshes, we get a much nicer approximation of the stress distribution. And this is actually something like the stresses, the von Mises stresses within this contact interface. Because it's von Mises stresses, you do not have the direct matching of the normal stresses in y direction. Okay, this is for the linear case. For the nonlinear case, a little bit more complicated. I did a little bit of a drawing here. What you have is at a certain instance, like here is sort of one point of the body above, you can do the projection for a time step n. And if you go to the next time step, of course, you have some sliding on the surface. And due to this, this point changes. So you always have to update somehow your virtual element mesh in a way, at least at this boundary, where you basically insert the new node. This is, of course, a little bit more complicated, but can be done even with friction. We have shown that I'm not going into the details here, but you can see if we want to run something like this, this is sort of what we call an ironing problem. So you have this little block, which is a little bit more stiff. So first you press it down. This is this situation here, and this is the stress distribution in y direction underneath. And then you start moving this thing on the surface while pressing down. And of course, you can see this is a large strain computation. So there is no, let me say, a scaling factor for the displacement field. So this is a real displacement. And you can see that we can move this block here over the surface. I have a nice movie, but with this kind of thing, it cannot show in my PDF viewer somehow doesn't like the Beamer movies inside. What you can see is that we get a certain reaction force. So first, when we press the whole thing down, we have a linear sort of incline of the reaction force. And then when we move it over the surface, so the reaction force sometimes goes away because here is less stiffness of the body underneath. So this makes sense. And this is the related frictional traction which comes with this movement somehow. Okay, so it works for contact. This is nice. At the moment, actually, we are working on the 3D extension of this kind of methods. The next thing is crack problems. This is also something which is very interesting for engineering, and we have worked in different areas here. It's linear elastic fracture mechanics, the phase field method for brittle and ductile fracture, and combined approaches, which we also use to, use where we coupled the phase field method with some fracture features. Classically, you can say, okay, why do we need all these kind of things? There's a lot of things already done. You can see it here. People have developed the XFEM, the damage mechanics, phase field, cohesive zone elements. A lot of things have been done. Classically, if you use a phase field approach, for example, you have to refine the mesh very much in the vicinity of the crack, because this method otherwise will not produce the correct result. The problem is that sometimes you don't know beforehand where the crack is and how the crack goes. So eventually you need some adaptive structures for that. Now, why could we use a virtual element method? The virtual element method has some sort of features which could be used quite nicely. We can split elements quite easily. We can even have elements like here on the right, where you have sort of a kink within the element. And this works quite nicely. So this is basically the idea. You can somehow compute the crack path by basically opening up here the crack somewhere in the element, and then basically look at and then sort of cut your mesh. Now, the question is, of course, how do you do this, and how can we compute here the crack opening and the sort of the direction in which the crack will go? And this can be done classically by what we call interaction integrals, or sort of not as general J integrals. With these J integrals, which are here, which are surface integrals. So you have to, if this is your crack tip here, you have to look around the crack tip and integrate around the crack tip some energy contributions, and this actually allows you to compute these the stress intensity factors, which are somehow depending on this interaction integral. Once you know the stress intensity factors, you can compute the shear stress at the crack tip, and you can also compute the propagation angle, so you know in which direction the crack will go. And finally, you can also say the crack propagates once your stress intensity factor is larger than the fracture toughness, which is a material property. Now, okay, this is sort of an extremely short view on the background, and the question is, does it work? So first, of course, we checked whether we can compute with the virtual element method here the crack intensity factors, and we used it in a mesh where we sort of put this stuff under tension and change the angle of the crack, of existing crack. And then there is actually an analytical solution in the linear fracture mechanics part. And you can see that our solution, which are the dots, are matching extremely well the theoretical values. So we can use this method, at least in our simulations. Now, of course, the next step is what we do. You have always in these methods to assume how long the crack, or what is the increment of the next crack. We can compute this angle here, as I have shown. So what we do, we establish some crack lengths, and then we compute a next node, for example, here, and insert the crack. Now, if in the next step we have a longer delta A, eventually we will end up within an element, and then we basically put the crack up to this inside the element and define this sort of very non-convex element with the crack. And then, of course, we have to keep going all the time. Let me just show this in this example. It's a classical example. You have initial crack here, and you have basically the shearing load here up there, and you want to compute the crack path. You can observe eventually that I have, or by purpose, we have sort of put in here some little animals instead of the classical Voronoi cells. This was only to show that we are able to compute even through these very complex shaped elements, the crack path. So you can see it here. When you start the crack path, sort of it opens up, and it nicely sort of bypasses all these animals, and it doesn't matter what shape of element you have, you can really compute the crack path. Now the question, of course, is this correct? And here you can see that depending on the delta A, depending on the number of elements you take, you get basically the correct curve, which is the crack opening via X, and this works quite well. So this is actually the crack path, which we can approximate. There's sort of a reference solution, and we approximate this quite nicely with our method. So this can be applied. And of course, we can also use, for more complex situations here, we pull this thing and we have two initial cracks here, and then you can see how the cracks basically move through the body for sort of an increase of the displacement field. And you can, of course, also see the stress field, which is, of course, concentrated around the tip. And also here, the animals do not stop the crack by moving through the solid. Now, of course, this is nice, but if you go 3D, it's very complicated to compute this interaction integral and the path. So the next step would be to use eventually the phase field method. And here I also advertise a talk by Fadi Aldakir this afternoon or today at lunchtime, where he talks about virtual elements in fracture mechanics. And I just want to show what we have done. So the idea was that we start with a coarse mesh, that we basically somehow refine and use at the crack tip actually something like the phase field method. That's what we want to do. So we have somehow to compute an error indicator, and we use here the phase field parameter to do that, which is without any proof, but it seems to work. We can then, by this error indicator, select a threshold of elements which we want to refine. Then we can do a refinement. We can use finite elements or virtual elements. And so we have this kind of refinement around the crack tip, which is basically then used to compute the phase field. And with the phase field method, we obtain automatically the correct direction of the crack path. Now, the idea is that we sort of follow the crack path. Once we have the crack introduced by the phase field method, we will open it up by our cutting procedure and then keep going with the crack path. So how does it work? We have again the same problem as before, like here. And now what we do is we basically refine the mesh around the crack tip by our error indicator. This is a solution with the phase field method. Now, then we basically cut the elements, which are basically here the red part, and introduce the crack and move at the same time the refinement together with the crack and keep going. So by this, actually, we have a very efficient method because we only need the refinement around the crack tip, and we can cut afterwards our elements by using our schemes, which we have developed and which is very easy when we use the phase field method. This one has not been done yet in 3D, but this is actually the way you have to go in 3D because their crack passes are very much more complicated and very hard to compute with using the interaction integral, and also very hard to compute even using XFEM or other methods. So this is sort of an advantage which we can take care of, which we have not done yet. Now, sorry about this, but another topic, homogenization. There, eventually what you want to do is you want to compute the properties of a macro material which you basically want to use for computation. But this macro material has a certain microstructure which has different constituents, and you want to basically be able to homogenize. I think yesterday Eduardo talked about this already. So what we want to do is we want actually to check whether we can use these virtual element scheme for homogenization. And this one here basically is all the methodology which you have to do. We have to basically apply some certain deformation modes and then on the microstructure, and then we can actually obtain the coefficients of the elasticity constants. Now, we made it a little bit more complicated. We have a polycrystalline material which has certain directions of anisotropy here, which you can compute or you can see. And the question is, does the virtual element method really works in this case? So basically, we tried this with different materials, which are autotropic and transversely anisotropic. We used here to characterize this the anisotropic index. Index equals 0 means isotropic. So this is weakly isotropic or almost isotropic, and this is really autotropic. And these different materials we sort of used to investigate that. And then, of course, you can also have the degree of the grain size with relation to the RVE size here. Now, this is what we got. we compared finite elements with virtual elements. Finite elements T2 means quadratic elements. And then we had a benchmark where we used a lot of T1 elements to basically compute the solution. And interestingly enough, this is a stiffness constant 1, 1, but you can also do it for the other constants. Interestingly enough, what happens is that the virtual element method always is as good as a reference solution, even better than the T2 discretization of this kind of method. Then this question is, of course, why is this the case? I mean, this is great because this means that we can use it for this homogenization purposes. And one idea is that when we use a coarse FEM mesh, you can see that the results of the stresses are very much scattered. This is sort of the stress field of the fine mesh. And this is a VEM mesh. And you can see actually that the VEM mesh reproduces the fine mesh results a lot better than the coarse finite element method. And this means that the VEM doesn't lock somehow in this response, and we get a very nice solution. So VEM is sort of the way to do homogenizations for polycrystalline materials. That's at least my conclusion in this case. And there will be a talk by Christoph Böhm today who will basically talk about multiphysics response of polycrystalline materials and the homogenization and apply all this kind of stuff to in the three-dimensional case where it really makes sense, because actually, to be frank, homogenization means you have to use to compute a three-dimensional material. Otherwise, you do not get the micro response correctly. Now we can go to crystal plasticity. Again, the question is, can we use a piece of polycrystal material, which is sort of on the micro scale, to compute also to homogenization problems using low order VEM? Crystal plasticity, instead of using something like this by sort of modeling the whole thing with finite elements, well, you can also use, of course, other meshes. We have done this before, it works, but the question, of course, is does the virtual element method also work? Now, I'm not going into the theory. The only thing I want to point out is that we have different sort of sliding directions which can be taken in crystal plasticity. So the plasticity can go in some directions. And of course, we are using here again first order VEM, which means a linear ansatz. That means a constant stress within each VEM element. And the question is, do we really get a good response with that? Because this is quite complex here. And the differences in all the polycrystals can be on, and these sliding planes can be different in the different parts. I'll jump over this and just go to the result. We have here some homogenized relation, which is the accumulative plastic shear. Here some result which we get when we apply certain periodic boundaries. And what is interesting here is we compared to a reference solution which was computed with quadratic tetrahedra elements, which more than 100,000 elements for this kind of piece here. And now we compared our method, which had basically 1,700 degrees of freedom, our Voronoi measure with each virtual element for one particle. And we compared it to a also linear element, which is a T1, and we call it O1, don't ask me why, and we refine. And what you can see here, this is the error with respect to the reference solution. This is what we get with VEM, and this is what you get with the classical finite element tetraheders. And this means that you are even better than using 40,000 degrees of freedom. So this is a good news, can be used. The other thing is, of course, the total solution time. VEM, of course, is slower than the classical normal triangles, but anyway, to get the same accuracy of solution, we need this type. But if you look this one, and this is actually a log scale, actually goes into the roof. It takes a very long time to compute and is not as good as what we get with the virtual element method. So there's a real big plus for the virtual element method in this regard. Now let me come to the plate, which is something which we looked at. We actually used something like, wanted to look at this from the point of view of anisotropic plates and check on that. We have actually taken, I think, from the paper of Donatella and Franco, the most simple elements. This is one element which is basically has the WH is cubic, which you have to choose, as also Franco pointed out. And then we have a linear relation, linear polynomial for the we call it zeta t, but it's basically the difference, the slope in normal direction. And we have another element which has quadratic, which is sort of more consistent because then the rotations are quadratic. Here, the one rotation is quadratic and the other one is linear. Now, the good thing is these elements are not used in engineering so much because they are, the good ones are very complicated. And the good thing is that they are locking free for thin plates. There's this old word from Keuter. It says all you need is love, meaning Kirchhoff love. And we can, of course, use these elements to compute something with orthotropic materials. You can see here the deformations, and for a solution with one ply, which has a certain direction of the stiffest component, or we can use a stack of ply and then we get some symmetric solution. So the element works quite nicely. Now the question is, of course, can we produce a finite element out of it? And the classical thing, we call it virtual element T1. This was the one which had sort of the linear slope for the normal, the normal slope in normal direction. And we have this quadratic element, which is sort of complete, has quadratic rotations and cubic deflections. And then there are, of course, a lot of elements which you can use. There are C1 continuous triangular elements, but you don't want to use them because the W, XX is actually something which as an unknown which you don't want. Now the performance of these elements. We use a stabilization which is like this. This is a classical stabilization. And what you can see here immediately is that the virtual element number 2 as a quadrilateral and as a triangle work extremely well. They work a lot better than classical finite elements which has been derived in the finite element area, which are basically pointwise conforming, non-conforming, but in this way. But then we also tried another stabilization, which is this integral over the boundary, which Blaž Hudobivnik came up with. And interestingly enough, what happens is that the simple element which we had, the simple triangular element, out of a sudden has a very good coarse mesh accuracy. The asymptotic accuracy is, of course, not as good as for the element number 2, but it has a good sort of coarse mesh accuracy, which you can also see here. Here we have the pointwise stabilization. It's clear that the elements number 2, the one which complete quadratic ansatz for the rotations, is very good. If you use here the continuous stabilization, out of a sudden, this guy here, the T1 element, the triangular element, is very good. It goes in this direction. Don't ask me why, but it works very well. And this is actually the element which engineers want to have because it only has rotations and deflections at the vertices. Engineers don't like so much, also in legacy code, the other thing. And now let me just run through the last thing, which is quite neat. So we have actually used the virtual element method for discrete element methods. As you can see here, we have designed different particles. Now these particles are flexible. So we actually checked, we compressed these particles and we checked whether we get basically a good performance of the stiffness. And there's a reference solution which we actually computed with Abacus. And you can see that the stiffness is quite okay for this beam. It's not so okay. And if you now look how we compressed it, the compression was quite high. And this is actually our virtual element. So it's compressed like this. It looks almost like having more, let me say, degrees of freedom or more elements. It's actually with constant strain inside and constant stress inside. It's sort of one element, but it performs quite well, as you can see here. Now, this has been used to compute, for example, the compaction of some sand particles in the box. You press it down, we can get the loading, unloading curves. And of course, this only can be done if you allow elasticity. Furthermore, we have taken a hopper and we have computed the outflow of the hopper. This is sort of the contact, it's a barrier contact formulation which we have used. And what you can see here is sort of first we fill in the hopper the particles so they sit here, and then comes the outflow. And the thing is, the rigid particles somehow clog and they don't flow out, whereas the flexible particles can be move out of the hopper. So flexibility sometimes helps you to escape whatever your problem. And with this, I like to close with a little picture, which is the art and the art of computing using BEM. And thank you very much.